This will be the last lesson for Chapter 9, and we're going to be focusing on another theory called the molecular orbital theory. Now, a number of years ago, I don't know if it's 3 or 4 or 5, maybe before COVID, molecular orbital theory was not on the AP test. But in the last couple of years, some students have remarked that there was a little bit of molecular orbital theory on the AP test. So I'm going to introduce this a little bit, but skip some of it. I want to familiarize you with the terminology and why we would have a second theory to explain bonding besides the one that we talked about in lesson number 2. So the molecular orbital theory, sometimes called the MO theory, which is not short for Missouri, assumes that pure atomic orbitals, which we've been talking about, in the molecule, combine to produce orbitals that are spread out or delocalized over several atoms. Now that's not going to make a whole lot of sense until we get into this in a little bit greater detail. So if you have 2 atomic orbitals, you will end up with 2 molecular orbitals. If you have 4 atomic orbitals, you will end up with 4 molecular orbitals. But again, we still haven't explained exactly what is a molecular orbital. And one of the reasons why we need an alternate theory of explanation is there are some things that our traditional approach using Lewis dot structures and valence electrons and so forth doesn't explain very well. And one of those has to do with the fact that if you have liquid oxygen, we're looking at this section right here, if you have liquid oxygen, it is paramagnetic, which implies that you have some unpaired electrons. So for example, the way that you were taught to draw the diatomic oxygen gas with its 12 valence electrons and therefore its 6 pairs is to first of all connect the 2 oxygens together. So there's 1 pair of electrons, and then you could say 2 pairs, 3 pairs, 4 pairs, 5 pairs, 6 pairs, and you notice the oxygen on the right does not have an octet. And so if we were to basically get rid of 1 pair of electron and stick it in the middle, and then spread out our pairs of electrons, like in this diagram right here, you can see that now each oxygen atom in diatomic oxygen has an octet around it, and it looks like it's trigonal planar around the pairs of electrons, the 3 regions of negativeness. But you'll notice that all the electrons are paired up, which would not therefore explain paramagnetism. And you're going to see later when we get to table 9.1 how the molecular orbital theory can explain how oxygen gas, at least in its liquid state, can be paramagnetic and affected by a strong magnetic field. So, continuing on, in the molecular orbital theory, we're going to talk about sets of molecular orbitals. And a set, of course, are going to contain 2 in this case. And one of the things that molecular orbital does is instead of thinking about orbitals as being occupied by dots, or electrons being particles, I should say, we're going to think about it as being a wave instead. So these orbitals are characterized as electron waves. Now, if you remember your freshman physics, you can have 1 wave, and then if you have another wave in the same place at the same time, they will reinforce each other, and you will get twice as high of a crest and twice as high of a trough. This would be considered constructive interference. When these 2 waves, when these 2 electrons constructively interfere with each other. But you can also have, and I'm going to erase that picture, you can also have, if the 2 electrons do not interfere with each other constructively, one wave, and then the other one is the opposite. And so your crest is going to combine with a trough, and the other trough is going to combine with a crest, and that's going to create a, if you will, a cancellation, a destructive interference. And that, in the new terminology, is going to be called an antibond. So when we have constructive interference, we're going to have bonding. And when we have destructive interference, we're going to have something called antibonding. Now, what exactly do we mean by that? So, if we think about our hydrogen nucleus and another hydrogen nucleus, and they each have one electron, and we can think of the attraction between the nuclei and the electrons. So I'm going to erase my two hydrogen atoms, and I'm going to replace those two hydrogen, the symbols for hydrogen atoms, with a blue dot representing the nucleus of a hydrogen atom. Of course, the nucleus of a hydrogen atom is going to be one proton. So if these two hydrogen atoms come together, you can see that this hydrogen atom on the left is going to be attracted to that electron and attracted to that electron, and this hydrogen atom on the right is attracted to that electron, and that's going to create forces that are going to want to pull them together. However, we can also say that these two electrons are going to repel each other, and these two nuclei are going to repel each other. But those forces of repulsion are going to be much weaker. And so the forces of repulsion are going to be weaker than the forces of attraction because of the proximity of the electrons being between the two positive nuclei. And so therefore the forces of attraction, I'll call that a positive force, is greater than the forces of repulsion, which is negative, and we can create a bond. Now, it's also possible, of course, that if these are my two hydrogen nuclei, my two protons, it is entirely possible that these electrons could be located outside, not in between the two positive neutrons. The probability of them being between the two protons is greater than the probability here. Nevertheless, it could happen. And in which case, you're going to have an attractive force right here, and an attractive force right there. You're going to have a repulsive force. I'm going to do the repulsive force in orange. Between these two protons, the two nuclei are going to have a strong proton force and a strong proton repulsive force between the two protons. And therefore the protonic repulsion, if you will, is going to be greater than the attractive force. And this is what we mean by an antibond. And in between this region of space and here, we have a zero probability of finding the electrons. This is what we mean by an antibond. This is where we have destructive interference, and this is where we have constructive interference. Now, these pictures right here show molecular orbitals for hydrogen, and we'll draw them in a minute. But the molecular orbital theory specifies that when you have a 1s orbital from one hydrogen atom and a 1s orbital from the other hydrogen atom, that's two atomic orbitals for the two atoms. They are going to create two molecular orbitals. One of them is going to be bonding, and one of them is going to be antibonding. And those are the two molecular orbitals that result from the two atomic orbitals. And before we continue with that discussion, the pictures right here in figure 912 just show you how oxygen gas, which can be created when you put your oxygen gas inside liquid nitrogen with a negative 196 degrees Celsius, the oxygen can turn into its liquid state. And then when you pour that oxygen over a strong magnet, you can see how the liquid oxygen adheres to the magnet. It's attracted. This is a neodymium magnet, which are very powerful magnets, and we use them a lot in physics, actually. Liquid nitrogen, by contrast, is diamagnetic. It wants to get away from the magnet. So liquid oxygen must have some unpaired electrons, and liquid nitrogen does not have any unpaired electrons. They must all be paired. Now let's see how that can be. So when we come over here, and we're going to talk about the electrons in hydrogen forming a bonding molecular orbital and then forming an anti-bonding molecular orbital. The bonding orbital is going to pull them together. The anti-bonding is going to cause the nuclei to repel, and we're going to look at the combination of both of these. And this is something that there is no counterpart in the valence bond theory to talking about anti-bonds. So the first principle, back up here, is that the number of atomic orbitals is going to give you the same number of molecular orbitals. The second principle is that the bonding molecular orbitals are lower in energy than the parent orbitals, and the anti-bonding orbitals are higher in energy than the parent orbitals. And in order to see that, come down to this diagram down here. If this is my 1s orbital from my one hydrogen atom, and this is my 1s orbital from the other hydrogen atom, I'm going to have a bonding orbital, which is at a lower energy level, because remember, energy increases along the y-axis, and I'm going to have an anti-bonding molecular orbital that is higher in energy. And if you remember that hydrogen gas is going to have 2 electrons total, one from each hydrogen, and we do the Aufbau principle and we begin to fill in my orbitals with these 2 electrons. I put 1 electron here, the second electron is going to be there, and I don't have any electrons left over to put in the anti-bonding molecular orbital. And so therefore, I have a molecular orbital diagram that shows a pair of electrons occupying this single covalent bond, and instead of calling it a 1s, we call it a sigma or 1s, a sigma bond. And there is no anti-bonding. And because we have bonding but no anti-bonding, hydrogen gas is a stable configuration, and hydrogen gas can exist. Now, when you blend these, this coming over to the left, when you blend these pictures together, your bonding orbital looks like this, and your anti-bonding creates this nodal plane in the middle because we're imagining the electrons. These dots here are protons in each hydrogen nucleus. These electrons here are on the outside rather than on the inside, like in the bonding. And therefore, this is not going to be a very, very stable bond configuration, and the likelihood of finding the electrons between my 2 nuclei is 0, creating what we call a nodal plane. You've seen the word nodal or nodal plane before when we were talking about the D and the F subshells. Now, we can ask ourselves the question, well, is it possible to have diatomic helium? Diatomic helium. And when we come over here to look at diatomic helium, H2, so whoops, let's get that E in there. 2. Each helium has 2 electrons, so this is going to be 4 electrons. And that means we're going to have 2 pairs of electrons. And we bring in our 1 helium atom, and we bring our other helium atom. These are my 2 atomic orbitals, 1, 2, and they're going to make 2 molecular orbitals, molecular orbital 1, molecular orbital 2. The bonding are at a lower energy level, meaning more stable. The antibonding at a higher energy level, meaning less stable. And when we begin to place our electrons, we put our first pair of electrons here, 1 from each helium. We put our second pair of electrons from each helium up here. And you can see that my bonding orbital is paired up. My anti-bonding orbital has a pair, and they cancel each other out. The bonding plus the anti-bonding gives me 0. And in which case this means that there is no reason for diatomic helium to exist, because the electrons positioned between the 2 nuclei, which would be attractive, are canceled out by the electrons on the outside of each helium nucleus, and that would be repulsive, and therefore that we would not expect there to be something such as diatomic helium. In a minute, we're going to be talking about bond order, and when your bond order equals 0, that means that we do not expect this type of molecule to exist. And just to jump ahead a little bit, bond order is defined as taking the number of electrons that are bonding and subtracting the number of electrons that are anti-bonding and multiplying it by 1/2. And so the number of electrons in diatomic helium that are bonding is 2, and the number of electrons that are anti-bonding is 2, and 2 minus 2 is 0 times 1/2, and we get a 0 bond order. So there is no net stability. We do not expect helium to be able to exist naturally under ordinary circumstances. Well, let's apply this to the dilithium molecule. Dilithium would be Li2, and that means we're going to be, bring 3 electrons to bear in our attempt to construct a molecule to see if this is possible. Dilithium crystals, by the way, and Starship Enterprise, as one of the ways that they powered the Starship in space when they were going into warp drive, where it's from their dilithium crystals. So let's look at that. So when we go to construct our energy levels, here is my 1s, and here is my 2s, and for the 1 helium, my 1 lithium, and on the other side I have my other lithium, the 1s and the 2s. So we have 4 atomic orbitals, and each lithium, of course, with its 3 electrons is going to have a 1s2 and then a 2s1. And so we have, with 2 lithiums, we're going to have 1, 2, and then with the next lithium, 3, 4 atomic orbitals, which are going to create 1, 2, 3, 4 molecular orbitals. And now with dilithium, we're going to have a total of 6 electrons, 3 for each. So beginning at the lowest energy level, we put my first pair, then my second pair, which is anti-bonding, and then my third pair, which is bonding. And we don't have any to put in the anti-bonding. And therefore, when we go to look at the possibility of stability for the dilithium crystal to exist, we see that these 2 cancel each other out, but these 2 can create a bond. Or if you want to look at it in terms of the bonding order, we have the number of bonding electrons, and this should be a 1 here, the number of bonding pairs here plus here, minus the antibonding. And let's double check that definition. The number of electrons in bonding and antibonding. I'm going to erase this. And so when we're looking at the number of bonding, we have 4 that are bonding, 2 plus 2, minus the 2 that are antibonding, right there, times 1/2. So 4 minus 2 is 2, times 1/2, that gives me a 1, and that's a positive number. So the dilithium crystal could theoretically exist. What about the helium-2 plus, diatomic helium with a positive charge? Is it possible for that to exist? And then down here we have our -1 possibility. Well, if you look at your bonding order, let's come back up to this diagram, and one of these electrons up here, we run out of electrons. So if we're talking about He2 with a plus sign, that's going to be a total of 2 electrons from the first helium and 2 electrons from the second helium, but a positive charge means we only have a 1 electron. So we have a total of, we have to take our 4 electrons and subtract 1 to get our 3. And so that's going to get rid of one of these electrons up here. And so we're going to have our 2 bonding electrons minus our anti-bonding electron times 1/2 is going to give me a 0.5. So theoretically, you could get a diatomic helium ion with a +1 charge. Now what about H2 minus? And in H2 minus, we go through the same scenario, but now we have an additional electron, and that additional electron is going to be anti-bonding. And so let's if we add that up, I'm double checking my thinking here. Going back to the He2 plus, there are 2 electrons in the bonding molecular orbital, only 1 in the anti-bonding. We have a positive 0.5. It's a weak bond, but it could exist. When we come down here, we're going to have our 5 electrons because we now have to add 1 for that negative charge. And when we combine our 1s orbitals, and then we go to our anti-bonding, and when we add these up, we're still going to get a 0.5 bond order. So there is going to be a possibility for this to exist. If we come back up here, it's because we're adding another electron up here when we talk about the total number of electrons. I think I said that right. Coming down here, molecular orbitals for lithium and beryllium. And here let's double check, make sure I did the third principle. Yeah, that had to do with bond order. By the way, you remember bond order from a previous chapter, previous section. This would be a bond order of 1, bond order of 2. A triple bond would be a bond order of 3. If you have a resonance structure like in benzene, actually you would have 1.5 bonds in between each of these carbons because of resonance, and you would have 1.5 bond order. So we're just applying bond order now to these molecular orbitals in lithium, diatomic lithium, and diatomic beryllium. Fourth principle of molecular orbital theory is that the atomic orbitals combine to form molecular orbitals most effectively when the atomic orbitals are of similar energy. And so now you have a few more examples that look at lithium diatomic lithium and diatomic beryllium, and whether or not your bond order is going to be positive or zero. When it's zero, the molecule is not going to exist. Also, you'll notice that we're only looking at the valence electrons, so we can ignore the core electrons. And for example, when we have beryllium is element number 4, but it only has 2 core electrons, and that would be in sigma 1s. And then it has 2 more electrons, and we create our sigma bonding and our sigma anti-bonding, and we place our electrons, and we go from there. So that gives you an idea of how we do the bonding and the anti-bonding. Every sigma bond and every pi bond that we make, we separate into a bonding orbital and an anti-bonding orbital. And you can create a sigma bond if your p orbital and your p orbital come together like this. But when they come together like this, that's going to be a different kind of bonding along the x and the y plane. And that's what's talked about down here. When they come in end to end, like is happening right here, here's my 1 pi p orbital that looks like a barbell in 3-dimensional space. That can create a sigma bond, both the molecular orbital and the anti-bonding molecular orbital. But they can also come in side by side. And when they come in side by side, instead of being sigma, bonding and anti-bonding, they are pi, bonding and anti-bonding. And if I could create another one, I can't draw it, where instead of being along the y-axis, imagine it being along the z-axis, coming out at you, and pretend that dot looks like an arrow coming up out of the page, and pretend that x looks like the tail of an arrow going into the page. This would also be side by side, but along the z plane instead of the y plane in 3-dimensional space. Now they start talking about dioxygen, which is diatomic oxygen, Brinkerhoff, O2, 6 electrons for each of the 2 atoms, which is a total of 12, which means we're going to have 6 pairs. And as you do your 6 pairs, you can see it in the second energy level. You put 2 in the 2s, you put 2 in the 2s anti-bonding, 2 in the 2p, and then you start to distribute them in the pi bonding, 2px, 2py, 2pz, and that's where the anti-bonding is going to come into play. And I'm going to jump to there we go, I'm looking for this. So here's my oxygen right there. And you'll notice that as we fill up our orbitals, we have the core down here. Don't show the core. There's my 2s, bonding, anti-bonding. P bonding, or pi bonding, pi anti-bonding. And then we go to the next pi, and we distribute our electrons, putting 1 in each orbital, Hund's rule, before we begin to pair them up. And you notice that now we have 2 electrons that are not paired. And those 2 electrons that are not paired can mean that this can be magnetic, which we see when oxygen is dense enough, like in its liquid state, and in proximity of a very strong magnet. You can see that fluorine, we predict, is not going to be paramagnetic because you do not see any electrons that are unpaired. Also, you'll notice that We use words like heteronuclear and homonuclear. Homonuclear means the two nuclei are the same, such as in Brinkelhoff, H2, N2, O2, F2, Cl2, and so forth. Heteronuclear diatomic molecules are where you have two different ones, like carbon monoxide, nitrogen monoxide. These would be heterodiatomic molecules. And can carbon monoxide exist? Well, we know from personal experience. By that I mean we know as human beings that carbon monoxide does exist because people have died of carbon monoxide poisoning. So and it's identified as such, so it must be stable. So if we look at carbon monoxide, carbon with its 4 valence electrons and oxygen with its 6 valence electrons, for a total of 10 valence electrons, there's 2 in the sigma bonding, 2 in the sigma anti-bonding. Then we go to the pi, and in the pi bonding, we have 4. And then over here we have another sigma bonding. We don't get to the pi anti-bonding or the 2p pi anti-bonding. And so when we look at this, we've got 2 and 6, and 2 gives me my 8. My anti-bonding, I have 2. 8 minus 2 is 6. 1/2 of 6 is 3. So this is a positive bond order, which means carbon monoxide is quite stable. And here's how that would look. Remember, instead of putting my 3p's side by side like we did with our 2x or my p sub x, p sub y, p sub z, what we're doing is creating one sigma bond, and then we are creating our pi bonds. We're not going to spend any time talking about resonance, and this is an interesting discussion of safe dyes and molecular orbitals, and how do we explain the azo group, which we find in an awful lot of dyes. We don't use it anymore because it's carcinogenic, which means it can be cancer causing. There's a person in the New Testament named Lydia who was a seller of purple dyes, and which means she's probably relatively wealthy. She comes to Christ through Paul's ministry. Where Paul was from, Tarsus, is in the, if you look at the Mediterranean Sea, along the northern shore on the very east, which is southern Turkey. Paul was from there, and that's where they would harvest thousands and thousands of these particular gastropods, or like clams, from which they could extract a little bit of this purple dye. And purple dye, therefore, because it was extraordinarily expensive, because it was so extraordinarily difficult to extract, only the very wealthy people could have purple dye. And that was true all the way up until the 19th century, when William Perkin figured out another way to make it, and now purple is relatively inexpensive. And we're going to stop this screencast at this point, and you can read more about it, but I think we covered enough for the AP.